Hello, bonsoir, Annie. Welcome to this Science North virtual star party. Happy summer solstice. My name is Aletha. I'm the staff scientist for Spaceplace and the Planetarium at Science North. And this is Lucy. There's Lucy.
Hello, everyone.
So Lucy is the science communicator for Spaceplace and the Planetarium. And we will be your host for this evening. And our special guest today is Dr. Raymond Francis.
Hello.
Hi, Raymond. Welcome. So Raymond actually grew up here in Sudbury, and now he's an engineer with the NASA Jet Propulsion Laboratory, and he's working with the Perseverance rover on Mars. So we are streaming to you today from Sudbury, Ontario, or Nswakamak. We are on the traditional and ancestral lands of the Atikameksheng, Anishinaabeg, and Wahnapitae First Nation. This land sits in the Robertson-Huron Treaty area. If you are joining us live, please share your location, the land you're on with us, as well as your comments and questions throughout the presentation and the night sky tour. Our topic this evening is artificial intelligence on Mars. And to get this party started, here's Raymond.
Hi. So we're going to talk a little bit about the kinds of artificial intelligence that we use in space exploration. We often talk about autonomy and intelligence kind of interchangeably. They're related but different concepts, and they're used for things like managing the spacecraft's onboard systems, just housekeeping, making sure that the heaters are turned on to keep the spacecraft alive, or autonomous navigation, whether it's on the surface of Mars or in free space in orbit. But I'm going to talk about a third use case, which is science, using intelligent systems to increase the amount of science, or science observations or science data that can be created by a mission and sent back to Earth. So I'm going to introduce you to the older now of the Mars rovers, Curiosity, which is still running, and it's on the surface of Mars since 2012. This is an actual photo of the rover taken by a camera on its robotic arm. That's what the rover really looks like. And this here is some of what we've done with that mission. You can see the long traverse, some 20 kilometers that we've driven on the surface here, exploring a bunch of places. We landed up near the top here, the so-called Bradbury Landing, and we've been driving down to the lower slopes of this mountain that we call Mount Sharp. That mountain exposes layers of rock that cover something like 2 billion years of the history of Mars, and this is what we came to study. And along the way, we've stopped and studied at each of these places that have names, and in fact, many more that we can't fit on the map. But we're there to do studies of the modern Martian environment, but also the ancient Martian environment, and the lake that used to be in this crater where we find ourselves, Gale Crater. And here you see rocks of different types here. These are sedimentary sandstones. This is a conglomerate. These are formed in water, in a little creek or in the lake bed. And we were able to show that these were formed underwater and in ancient, what we call lacustrine environments, because of the chemistry, not just these morphological features, the shape and the layering, but the actual detailed geochemistry. And a main way that we measure that is with an instrument called ChemCam. This is for chemistry and camera, and it's something that we've used to make hundreds of thousands of measurements of different places on the surface. One thing that people like to hear about ChemCam is that in addition to the cam part is the chem, and we get the chemistry using a powerful laser. We have a laser-induced breakdown spectrometer. We focus this laser on through this telescope that you see here on targets that are up to 7 meters away from the rover and vaporize the surface of the rock. You can see down here 9 little spots that were burned by the laser. And when you vaporize the rock, it creates a plasma that glows in certain wavelengths, and you can tell from those wavelengths what the rock is made of. We get the atomic composition of the rock. So the one thing about ChemCam is that you have to point it. You have to choose where to point it because it's a pinpoint laser measurement. So you really need humans on Earth to decide where to point this instrument. A wide field camera, you can just point and make big mosaics and send them down to Earth and study them. But ChemCam is making very narrow field measurements, so it needs to be pointed with thought and care. So, like I say, we use this all the time, but there's a challenge with ChemCam. So we don't drive every day with the rover, but many days we drive. And this is a diagram of the schedule of a day on Mars. The drive is here in pink. We upload the whole plan for this day at once after we plan out what we're going to do for this day. Before the drive, we can take the images that we already have of the place that the rover's at, point ChemCam at anything we see there. And we can also place the rover's robotic arm on such things. But then we drive, and then after the drive, we're going to be in a new place. We don't know where. We don't have images of that place because we haven't been there yet. When we plan out this day, we don't have those pictures. So after the drive, there's lots of time here when the rover is awake and turned on, and there's power available and sunlight available to do observations, but we don't have any idea what's around the rover. So people on Earth cannot choose targets for ChemCam. So we either have to find something else to do at this time, and that's what we did originally, was just do what we call untargeted measurements, take pictures of the sun or the sky or the ground without any targeting. But for ChemCam, it's really hard because you have to point that. So the solution was artificial intelligence. And we came up with a system called Aegis. The Aegis is this intelligent software system that we've been running now for just over 5 years aboard the Curiosity rover. And what Aegis does is it autonomously selects science targets for the rover, which is to say rocks, geological targets that are worth measuring with ChemCam, and points ChemCam and fires the laser at those targets without anyone on Earth knowing what's happening. We get the results afterwards. It also chooses its targets based on preferences that were encoded into the software and are by the scientists and can be adjusted at each cycle. Every time we send up an Aegis activity to the rover, the scientists can adjust their parameters for what's the best kind of rock today. And to do this, if you know anything about computer vision, you know that this is really challenging. These are natural scenes. This isn't like recognizing a standardized object in a standard environment. Rocks come in all kinds of shapes and colors and sizes, and the environments here are changing every day as we drive into new unexplored terrain. So how do we do this a little bit? I should say first, even pointing ChemCam comes with its own challenges. Not only do you have to pick a good rock, but you have to pick rocks that are safe for ChemCam. We have a constraint with ChemCam not to point the instrument too close to the sun because you could damage it. ChemCam looks through a powerful telescope, and for the same reason you should not look at the sun through a telescope with your eyes, ChemCam should not look at the sun through its telescope, because too much solar energy will be concentrated inside the instrument and damage it. So you not only cannot look at the sun, but you can't look within several degrees of the sun. And these yellow bands here tell you where is not safe. So when we're autonomously, robotically, intelligent software pointing the instrument around, we have to make sure that the software does not point the instrument anywhere near these sun exclusion zones. So that's to protect the instrument. But ChemCam is also a powerful laser that can vaporize the surface of rocks. So we also have to protect the rover. We can't shoot the rover with ChemCam. And in fact, much of the rover is visible to ChemCam. If you look on the right, this is a sort of polar projection image of what parts of the rover are visible to the instrument. And in fact, there's some more over here that's just not shown. But anyway, all these places in red are places that ChemCam must not shoot. And because if you look on the left, this is what happens when you shoot ChemCam's powerful laser at a plate made of solid titanium. You end up with craters in it from the powerful laser. And this is a part of the rover. This is the calibration target for ChemCam. It's the only part of the rover you're allowed to shoot. And you see we shoot it fairly regularly. Anyway, so it's not just about finding a good rock. It's also about making sure you don't accidentally mistake part of the rover for a rock or point the instrument too close to the sun. So what Aegis does is it takes images with the nav cam or with ChemCam's own context camera, the RMI, the remote micro imager. And then using a computer vision algorithm, is one that's very sensitive to edges, and in particular edges that you can close into a loop, finds rocks in the image. And we can, because we're on Mars, we can make the assumption that just about any object that you can find a clear edge all the way around, it's probably a rock. This wouldn't work in a city. There are many other objects besides rocks, but on Mars, we can make that assumption. And then you look inside that rock for various image properties: how bright, how dark, what shape is it, how consistent is the color, these kind of things. And then you can filter out targets that are too far for ChemCam or too close to the rover, or maybe they're too small.
Oh my gosh, I don't know if it's a joke, Raymond, but we've got Mandela asking, I thought this was an intelligent science show. Why are you talking science fiction? It does seem like that, right? Lasers on Mars, artificial intelligence on Mars, but
this is all real. These are, you're right now looking at real pictures from Mars. The only thing that's not a real picture from Mars is this one here. These are pebbles in the Mars yard on Earth. This was used for testing the software, but all the other, this is an actual picture from Mars, and so are these. This is real. But yeah, so you know the software filters out rocks that we think wouldn't be good. Often this edge detection software, I'll let you in on a secret. It's really good at finding teeny tiny little rocks, and we don't want to measure those. So we just filter out the teeny ones and reject the ones we don't like, and then rank these according to which are most like the thing the scientists ask for. And honestly, it's just an algebraic equation that you optimize.
So are you mostly looking just for rocks? Because I know, like before a lot of times before it had the artificial intelligence, it would just kind of randomly shoot lasers, but sometimes it would hit soil a lot, which isn't as interesting as rocks. So are we mostly trying to find large rocks, or are there like properties of the rocks that are also?
Yeah, one thing that we usually do is we ask it to try and find rocks that look like they're still in the place where they formed, like the bedrock. And so rocks that are in place as opposed to loose rocks. Although if you don't have any of that, then the loose rocks are good enough. And usually, yeah, we prefer the rock over the soil because you don't know where that sand came from. It was made somewhere. It eroded out of someplace else. It's been blown around by the wind. The composition of the sand is interesting to some of the scientists, but if you really want to solve the big geological puzzles, you want to understand not just what a rock is made of, but everything that the context of its position tells you.
Because you're exploring, you're like kind of trying to create a map in a sense.
Exactly, yeah. And some loose rock that isn't connected to its place of origin, that could be from anywhere. It could literally have fallen out of the sky. So it's usually better to look for rocks that are in place. And the scene profile, as we call it, that the scientists most commonly use is the one that looks for outcrops. But yeah, this is what we do, and we place a sort of we find the coordinates of this rock and place a coordinate frame there, and the rover then points there, and then there you go. You make a ChemCam measurement, and that's how it looks. You can also loop it back, set a different set of priorities, and run another cycle if you want. But just to give you an idea of what this looks like, these are the kinds of images that Aegis is using. They're black and white, 1 megapixel NavCam images from the Curiosity rover. And what you're seeing here are plots of traces of all the outlines of the targets. And everything in blue is a target that was found. Everything in red is a target that survived the filtering. And then the targets that were actually measured are filled in green or orange if there are 2 targets. Sometimes we get 2 at once if there's enough time. And so these give you an idea of just how diverse the scenes are. Here you've got large rocks which have shadows, with many little rocks in between. And there's only 1 patch of outcrop in the whole place, and Aegis found it right here. But then here on the right, you have an area where there's lots and lots of outcrop, and Aegis has to parse that and find a piece of it that's not covered in sand or other, or too dusty and reasonable to measure. And here there are 2 of these targets. The little yellow dots, by the way, are where the actual ChemCam measurement was made. I mean, you can see the terrain varies a lot from day to day as we drive around. And I've got a second set of images here of the same type. And another problem you have to deal with is sometimes the shadow of the rover actually comes into the scene. And so you have to make sure that you don't mistake that for a rock or get confused by that. So anyway, these are the kinds of things that we do. And ChemCam has now made over 300 targets with Aegis, each of them with hundreds of spectra. So we have like quite a large part of the ChemCam catalog of observations at this point has actually come from artificially intelligently targeted measurements with Aegis. So it's become a big part.
Aegis isn't just targeting and then you're seeing the picture and you're like, okay, yeah, let's go ahead and sample there. This work is all happening in a time that would have normally sort of been downtime or would have been random sampling. And these pictures are just sort of showing you what was done and why.
Exactly. Right? Yeah. Humans on Earth do not vet Aegis's results. Aegis picks a target and immediately measures it with ChemCam a moment later. And then we get the results, both the image and the geochemical spectra later at the next opportunity for downlink from Mars. And yeah, so it's all autonomous. It's not just picking rocks for humans to approve. It really does this all by itself. Anyway, that's sort of what I had to show about Aegis. Awesome. I guess the one other thing is to say that we do this on a really, really lightweight computer. We're running on a computer that it's called the RAD 750. It is the main computer on the rover. That thing is basically what was in your desktop computer in 1995. It's running at 133 megahertz. We have access to 16 megabytes of RAM, and we have to do all of this in that little teeny tiny computer. So yeah, that's the resources we have, and we have to fit in there. That's part of the reason we've all 1 megapixel images. Yeah.
We've all got these. And actually, speaking of our mobile devices, if you have a mobile device handy, I'd love for you to pull it out right now, because we've come to a section where we can actually have some audience engagement using Mentimeter. So this was a very cool presentation. I'm sure it probably brought up a few questions, and people might also just have questions. They might just want to ask you about working with Perseverance as well, because Perseverance is also using AI technology, and so we can talk a bit about that. And
yeah, that's right. And in fact, in many ways more advanced than what we have on Curiosity. And we will be rolling out Aegis very soon on Perseverance.
Oh, we do have, and here's our first question. Okay, we'll answer this before we start quizzing you. Mm-hmm. But in the meantime, if you can go to Mentimeter, www.menti.com. We can pull up a slide in a moment that has that website on it for you. And you'll just go to the website, punch in a code, and you'll be able to engage with us. We'll be able to see your answers. We're going to quiz you on what you just learned, as well as some sort of general space stuff. So, and also I think we can drop the link in the chat as well. There it is. Awesome. Okay, so Juan Pablo, who I believe is from Chile. So we have people joining us from Iowa, from Texas, from Chile, as well as, of course, our Sudbury audience. So this is pretty cool. All right, so the question is, are more neutrinos received at the solstice? That's an interesting question. Oh, and we have people from Brazil. Gotta remember, Brazil. Yes. I'm wondering about that. So we get neutrinos from the sun. I don't really think we'd get more during the summer solstice. Maybe like in the northern hemisphere because we're getting more daylight, but the neutrinos, they go right through the planet. So I don't think like us being tilted towards it matters all that much. What do you think, Raymond?
Yeah, I think that's right. And I think, you know, the vast number of neutrinos that are coming through, the huge numbers of them in the orders of magnitude, you know, as you say, mostly they just fly right through. And the tiny fraction that are actually caught by neutrino detectors, I expect that the noise in that signal is much larger than any variation in the Earth's attitude would affect.
Yeah, we probably can't measure it. All right. Okay, let's bring up our first question, our first poll. We're going to do a couple that aren't worth any points, just so everyone can get on board and make sure we're all caught up with everything. This one is just very broad. We want to know what you celebrate around the summer solstice, and you can choose as many as you want, all the things that you celebrate. So go ahead, you can see up at the top, menti.com, and then our code 9510273. So you just want to, Raymond, I don't know if it's fair for you to play. No, you can play. You can play. Awesome. Okay. Oh, we're getting some answers already. Okay. So this is I'm going to admit this. This is my first time using this. So I'm excited to see how it's going to go.
Looks like this question is either or, so you got to pick one.
Oh no, I'm so sorry. See, first time. Now I'm learning.
That's all right.
Okay, so you got to choose the thing that you want to celebrate the most. Summer solstice, good, nice. You know what I'm finding on my phone, when I pull this up, it's giving me like my phone number pad, but it still works. It's okay. Like I feel like I'm going to dial a phone number. All right. Okay, so we've got 5 people on. That's pretty good. And 5 people went, okay. All right. Well, this is just the warm up. So we're gonna go to the next one. I will let you know that Science North's birthday, that wasn't a trick. This is actually Science North's birthday. Yeah, Science North turned 37 today. So June 19th, we celebrate. So that's kind of fun that it's close to the solstice. And of course, we also celebrate National Indigenous Peoples Day. Very exciting time. Yes, here in Sudbury, we have great celebrations. It's a little different now with COVID, but all right, next slide. Here we go. Okay, now we're getting a little more. This still isn't worth points, but we're seeing if you were paying attention. Now we know that you don't get to decide, really, but if you did receive this image of the Martian surface from Aegis, I want you to drop a pin where you would want the sample to be taken from. Yeah. Okay, you were listening. Very good. Nice. So we know that is outlining a rock, right, in amongst all this sand, which is pretty neat. So, Raymond, what do you think? Like with this kind of ability, with this kind of capacity, and we know it's going to grow, is there still a place for human explorers to be out there choosing which rocks to sample?
Oh, absolutely. And in fact, whenever the humans can choose the targets, we have them do it because they can process, like, humans can look through several images at once and say, oh, this image has a good rock. Let me point over here. He just takes one picture, picks what's best, does that. And there's also a bit of a cost associated with running Aegis. We have to spend a few minutes capturing the navcam image and computing on it. And with that crummy computer I described, it takes like 4 to 10 minutes to crunch the numbers. And that's time we could use to make an observation with another observation with ChemCam. But when humans can't be there, then this is your best choice.
All right, so listen up, kids. This is one of the jobs that AI cannot completely replace and take over the human in. So you may have a future in space exploration. Okay, now we're getting into the points. Here we go. Okay, we're going to start the countdown now. So Aegis stands for, it's going to be multiple choice. autonomous exploration for gathering increased science, always educating girls in science, or action, Earthlings in space. Make your choice.
And this is a sneaky first question because I didn't say it out loud. It was on the slide.
Nope. Ooh, but we had a very attentive audience. Way to go. Congratulations. I am super impressed. Okay.
Excellent.
Here's our leaderboard, and it's pretty much all neck and neck here. Very good. Okay, and so you can see a difference there. That's just how fast you answer. So answer the next one as quick as you can. Here we go. Okay, and this is actually, we have a question in the chat that this kind of relates to. So Earth has seasons because of our distance from the sun changing, the tilt on our axis of spin, or the sun changing temperature. What do you think? Nice. Well done. And somebody's learning something new, which is always awesome. Okay, here we go. Last question. Leaderboard first, of course. Ivy in the lead, very fast. Hey, does Mars have seasons? This is yes or no. Get in there, or sometimes. You can say sometimes. Well done. Awesome. Good job, folks. Okay. I'm going to stop sharing that now and figure out how to turn off this music. Oh, wait, I don't want to stop sharing yet. We have to see the leaderboard. That's how I'm new at this. Okay. There we go. Not full screen, but we can see that Ivy won, followed by Dragonite and Dr. B. And well done, everyone. Thank you very much for playing. Okay, now I got to get the music to stop.
So an interesting note about that second question. We asked, why does the Earth have seasons, right? Mm-hmm. We got the answer.
Yeah.
The answer is different for Mars.
Ooh, that's interesting. And okay, and so we've also in the chat we've had someone ask if Mars has a solstice, and I think this is all going to be related. So I'm really looking forward to what you have to say here. Yeah.
So we said that the Earth had seasons because of its axial tilt, and that's right. That's a conventional and correct answer. The northern hemisphere of the Earth is tilted towards the sun more in sort of June and July than it is in December and January. Yeah, here, this is why these globes are all tilted at about 23 degrees. But Mars is also tilted almost the same amount. It's about 23 degrees. But Mars also has a much more eccentric orbit than the Earth. And so it actually travels farther away from the sun. The distance from Mars to the sun varies more than it does for the Earth. And it's enough that it actually is almost as strong a signal as the axial tilt. In fact, there's a weather phenomenon on Mars that only appears when Mars is far from the sun. We call it the Aphelion cloud belt. The upper atmosphere near the equator gets cool enough that you get clouds, but only during that part of Mars's orbit when Mars is farther from the sun. And so on Mars, the answer is both the axial tilt and the distance from the sun, where on Earth, the orbit is so circular that there isn't that much difference from in the...
Right, and like here in summer, the northern hemisphere summer, we're actually a bit closer. We're more closer to perigee than we are in winter. And we went over that on the last overview. We talked about this, how to remember the difference between apogee and perigee. So EP, like apart, Perigee, you're farther away. And wait, yes.
Yeah, perigee is close.
And then Peri, yeah. Okay. This has been very fun. Oh, we have another one. Is it possible that climate change, we will have only two, with climate change, will we only have 2 seasons in the future?
I hope not.
We are really committed to limiting the warming to 1.5 degrees, which is 0.5 above where we are now, because we've already warmed it by 1 degree. And so hopefully not. I wonder what that would look like, though. If it got warmer, would it just kind of be 2 seasons, or?
I think, you know, that you can do like the 0th order physics class model. It just says, well, what if we just evenly warmed everything up by, you know, 2 degrees or 10 degrees, or pick any.
We know it doesn't work like that, right? There's areas that are heating up much faster, like the poles are like the North Pole is heating up much faster, and the land is heating up faster than the water.
Exactly. And so once you apply these models to the real Earth, suddenly like, oh, do we change the circulation in the oceans? Do we change the circulation in the atmosphere? And so this, like the weather completely changes.
That's kind of why it's starting to be called like climate chaos, right?
Exactly. And that's part of the reason that while we can predict the overall average amount of warming really well, predicting the extreme changes in specific locations is really hard.
Really hard.
Yeah. So basically it's, you know, significant global average warming results in a situation that is very difficult to understand, and you should not run a non-understood experiment on a thing you have to live in.
And I'm excited to get to the night sky tour to bring Lucy in here, but I am curious, like when we're studying Mars, are we learning things about Earth too, and maybe about our climate? Like one thing we've learned, right, is that at one time we think Mars was habitable and now it's not. So we know that's a possibility for planets, right?
Yeah. And what happened, in fact, you know, ancient Mars looked a lot like Earth, warm, water all over the surface, rocks beginning to form, sedimentary rock cycles happening. And it seems like Venus was really similar. And Venus may be even more similar to the Earth in ancient times of a few billion years ago. Similar surface gravity, similar size of planet. But now something on Venus triggered a runaway greenhouse effect, where now surface temperature is hundreds of degrees Celsius warmer than it is Earth. And the environment is, something happened to the climate of those two planets that drove them in very different directions than the Earth.
Yeah. And like we know Venus, even though it's not the closest planet to the sun, Mercury is closest to the sun, but Venus is hottest because of its greenhouse effect. So that is one of the ways we learned about it. Okay, this is all really interesting, but I know especially our Sudbury viewers would like to know what they can see in the night sky tonight, including Mars. So let's bring in Lucy.
Hello, everyone. So let's take a look at our night sky. I'm still using, again, stellarium-web.org, which is in the description. The link is in there. It's a free browser-based program that you can use to take a look at the night sky at any time. And we're looking at the night sky before 11 at this point here. I can go back a bit in time. So the sun sets really late this time of year since we are so close to the summer solstice. So the sun sets tonight in Sudbury at 9:20, which means if you wait an hour after the sun sets, it's still kind of bright-ish. So usually you want to wait at least an hour after the sun sets for it to get dark enough. Here I have an hour and a bit after sunsets where we can see a bit more stars. And we are looking towards the south, and we get to see our lovely moon tonight. It is just past a quarter moon, but if we look towards the west, we can see a few planets right after the sun sets. So right over the horizon, we can see Venus is going to be setting soon, but we also see Mars. Now, because of this landscape, it's kind of blocking Mars. So if I just make the landscape kind of invisible for a moment, that's what Mars would look like. Mars is a nice reddish dot in the night sky because of its surface. It reflects a lot of the red color, so we do get to see Mars in the night sky tonight. We won't be seeing it for very long, though. Soon enough, it'll be below the horizon after the sun sets. Now, let's take a look at a few constellations. I like to start with some of the brighter stars. You might know which one I'll be starting with if you've seen this before. So we're looking towards the north here in the northern hemisphere. If we look towards the north, we can see some nice bright grouping of stars. We get to see over here a handle in a pot area. So this is the Big Dipper, which happens to be part of a constellation. So we do have Ursa Major, the Big Bear, and we can use the Big Dipper to do a bit of star hopping. Let's in fact just go a little later at night, so maybe it'll be a bit darker. We can see a bit more stars now. Remember, if you're near any towns and cities, you won't be able to see as many stars. There's too much light pollution.
Are we
Yeah,
seeing a Starlink? Is that Starlink?
I think it is. We are. So we're seeing the nice
So
little.
has anyone
Starlink.
let us know in the chat or in the comments if you've seen Starlink in the night sky, if you've seen this sort of trail of satellites?
You'll be able to see it tonight at 10:50 if it's nice and clear out and there's no clouds in the way.
50, that's very cool. I have to let my neighbor know. She was just asking me. Oh, we've got Juan is actually, he's in Chile, which is, he's just mentioned that's one of the best places to observe the sky at the ALMA telescope. And that is absolutely true. And we have another question, which I'm finding kind of interesting. So it was about what happens if we get a solar storm during the summer. So this is a question from Juan. And does it, is there more of an effect for us in the Northern Hemisphere if we're getting a solar storm during the summer?
That's a very good question. I'm not sure exactly of if it's going to be more or less of an effect, but if we do have enough of a solar storm to which we're going to have auroras, it's going to be a bit harder to see during the summer since the sun sets so late. It will have less of a night's time to actually see it. So I know for us, it's usually easier to see the auroras when it's winter time. The sun sets a bit earlier, well, much earlier at this point, and you'll get to see it a bit better. But I'm not sure if it'll have more or less of an effect. That I'm not too sure about.
I don't think we're particularly more at risk from solar storms in the summertime. I think it's pretty.
It also fluctuates too with the sun. It has kind of like quite a few year cycles too.
Well, those Starlings are super cool. All right, let's get back to the tour. Let's see, what can we see up there?
So we are still looking at, well, it went pretty much through the next constellation I was going to show you. Using the Big Dipper, which is part of the Big Bear, we can do some star hopping. The easiest way to find a bunch of stars and a bunch of constellations in the sky is to start with some of the bright ones and star hop from there. So if we take the two stars right at the edge of the pot, we can follow the imaginary line it makes to this brightish star. Not the brightest star, though, but still fairly bright. It happens to be part of its own grouping of stars, which it doesn't have that many bright stars. These over here are not that bright, but we have Ursa Minor, or the Little Bear, and that bright star we star hop to, that is known as Polaris, or the North Star. So in the northern hemisphere, if you're looking towards the north, you can find the Big Dipper and Polaris. You'll know that you're facing north since Polaris, the North Star, is right above the North Pole. So no matter what time of year it is, what time of night, if you can find it, you know for sure you'll be facing north, and it helps with navigation. That's what people have used for a very long time to help with navigation during the nighttime. And then from here, we can take a bit of time to do a bit more star hopping, see some of the other constellations. So let's kind of angle out over this way. Let's take the Big Dipper and take the handle this time. And we're going to arc down to Arcturus. Nice bright star in the night sky. It is part of Boötes. He is a herdsman. And from there, we can spike down to this bright star in Virgo known as Spica. So really good tricks to use. Arcturus, spike to Spica. And we have here a zodiac sign. Virgo is one of the zodiac signs. It's along what's known as the ecliptic, this imaginary line through space where the sun and the planets are traveling along. So we do have Mars and Venus over on this side. They are along the ecliptic. So is the moon. And we do have we got to see this in the past. It's known as a spring constellation. If we find this kind of like looks like almost like a reverse question mark and this triangle, it is part of and makes up Leo the lion. However, we are now starting to see some of the summer constellations since, well, the summer solstice marks the first day of summer. If we look further towards the southwest, next to Virgo, we have, okay, this one's a bit harder to find, doesn't have as many bright stars, but we do have Libra, which are the scales. But next to that, we have Scorpius that's going to start showing up. So Scorpius is a scorpion, and it's a very fun one to find because it does have a nice bright star in it, or a reddish star, red supergiant star known as Antares. It was called that back in the day when the Greeks and Romans were making star charts to help people remember that this was not Mars. Mars is a reddish planet, so it looks like a red dot in the night sky, and it travels along the ecliptic, along the zodiac signs. Well, Antares is in a zodiac sign, and it's a reddish star, so a lot of people would mistake it for Mars. So they called it Antares, which means literally not Mars. Since Mars is the Roman god of war, Ares is the Greek god of war. So they pretty much mean the same thing. So, Olathe, were there any other questions during that little bit?
We don't have any other questions, but we are reminded that in Chile, winter is starting. So it's kind of
yes. So in the southern hemisphere, it's the opposite. So it's the winter solstice coming up, and winter is going to start, which is wonderful. Now, let's head quickly over back to the Big Dipper. We can do some more star hopping in the other direction. So if I'll take away the constellations and the lines, you can see how it'll look like without them. We have some stars in between the Big Dipper and the Little Dipper that curves back over here, makes a square here that makes kind of like a head and a long body of Draco the Dragon. And his head is really close to this really bright star known as Vega. It's part of Lyra, which is a harp-ish, a lyre. That's what it is. It's a lyre, a music instrument, and I find it does look kind of like, if we link these stars here, it looks like a tie or a fish. So if you can find that in the sky, you know that you're looking at Lyra. And this happens to be part of what's known as the Summer Triangle. So it's another asterism, like how the Big Dipper is an asterism. It's part of another constellation. So it's part of the Big Bear, Ursa Major. The Summer Triangle actually has a star in 3 constellations. So there's Vega. We also have Deneb and Altair, which makes this summer triangle, this nice big triangle in the sky. Here it looks fairly small, but it'll look much bigger outside. So it makes up, well, Vega is part of Lyra. Deneb is part of Cygnus, which is a swan, so it has two nice big wings. And Altair is part of what's known as Aquila, which is an eagle. So we do have the summer triangle here.
Definitely a good one to start with. That is awesome.
Exactly.
Thank you very much, Lucy.
We
do have another question. Juan is asking, so the planet Uranus rotates about a horizontal axis. So we know that Uranus is sort of more like relative to the sun, it's more spinning kind of like this. What would the seasons be like if our planet rotated that way? And I'm going to pass this one back to Raymond. I bet you have some interesting ideas on it. And I have a fun. Can I share the story, Raymond, about science? So when I first met Raymond, he totally blew me away because he grew up here in Sudbury, and he said, I love Science North. I keep my membership up to date, and I actually applied for your job. I applied to be the staff scientist for Space Place and Planetarium. And did you get an interview?
No.
So, and then you got this amazing job. So this another thing, like, kids, you might not get the first job you apply for, the second job you apply for, but you might get a way cooler job. So, like, keep going for it. You never know where you're going to end up. But Raymond is, I think, a science communicator at heart, and why he's so gracious and joins us for these talks. So, Raymond, what are your thoughts on this?
So we're still in the early days of studying Uranus and its climate. This is Uranus. It's kind of like Jupiter and Saturn in that it's a very gaseous planet, although its composition is a little different. And it's a big ball of rotating gas, but which means that seasons there are very important. Like the solid part of a planet doesn't change all that much when the seasons change, but the gaseous part absolutely does. And so it would be very important there. But Uranus we expect has extreme seasonality because it's so strongly tilted, like about 100 degrees away from normal to the ecliptic, as we say, from what you might call vertical. Anyway, what would it be like on Earth? You would expect extreme seasonality. You would expect that there would be wide swings in temperature and huge movement of water, for example, from one pole to the other. That's even on Mars, that already happens. I think, without making any specifics, because it's really hard to conjecture, you would expect extreme changes from one season to the other in temperature and how much water and ice there is in different places. It would be difficult for living things.
Well, thank you. It is kind of an amazing set of circumstances that allow there to be life on Earth, right? It's not something to take for granted. I even learned the other day that if we didn't have the impact with Theia that created the moon, we might not have had enough of a magnetic shield to, like, preserve our atmosphere. So it's sort of an amazing number of things that came together that allow us to live here on the planet, which is just fabulous. So I'm going to wrap up. We've gone over time, but well worth it. Raymond, thank you so much for joining us. It's been an absolute pleasure, as always. Is there any last thing you'd like to share with our audience?
Yeah, I think, even if the sun sets very late, especially in northern latitudes this month, it's worth a look in the evenings. As you saw, the planets are visible. 3 new missions to Venus were just announced, and we have several missions currently at Mars. When you look at that red spot, not Antares, but Ares itself, when you look at that spot, know that is a planet with several working robots on it right now. That's a real place.
Very cool. Thank you so much for joining us. And thank you to everyone who joined us online here and who participated and asked questions. It really makes it when you join in like this. And if you liked this content, please donate, like, and subscribe for more. We are looking forward to an in-person star party at Science North on Saturday, July 3rd. If everything goes well. And next month, Saturday, July 17th, Cassandra Marion from the Canada Aviation and Space Museum and Kirsten Van Stone from the Fields Institute will be joining us for another virtual star party to talk about the role of imagination in space exploration. Thank you. Merci. Keep looking up.
Bye, everyone.